Welcome to this explainer. Today we're unpacking a defining moment in modern industrial history, the Deepwater Horizon disaster. Look, we aren't looking at this just because it was some unrepeatable freak occurrence. We're looking at it because it was a devastating convergence of mistakes. Mistakes that actually happen at varying scales in our industry all the time. This event fundamentally changed offshore operations, and unpacking what went wrong reveals a whole lot about the daily engineering decisions we all make.
You've probably seen this image. It is completely burned into the collective memory of the industry. On April 20th, 2010, the Deepwater Horizon, which was this highly advanced, fifth-generation, dynamically positioned semi-submersible drilling rig, suffered a catastrophic blowout in the Gulf of Mexico. A massive explosion of escaping methane gas literally tore through the platform. The resulting fireball killed 11 workers out of the 126 on board, and it injured 17 others. It was an absolute human tragedy that just rocked the oil industry back on its heels.
But the nightmare didn't stop on April 20th. 87. Let that sink in for a second. That is the agonizing number of days it took for responders to finally seal this well at the bottom of the ocean. For almost 3 solid months, the entire world watched as every single initial attempt to cap the well completely failed. Which leads us directly to this staggering figure, 4.9 million. During those 87 days, the ruptured well released approximately 4.9 million barrels of crude oil right into the Gulf of Mexico. This wasn't just an industrial accident. It created the largest marine oil spill in recorded history. It devastated wildlife, ruined coastal environments, and destroyed the livelihoods of people relying on fishing and tourism. To understand how something of this magnitude could even happen, we have to peel back the layers of what safety experts call the Swiss cheese failure model. Let's start peeling back that first layer in Section 1, the cementing failure.
To figure out the root technical cause here, we really have to look at the specific operation they were doing. They were in the middle of temporarily abandoning the Macondo well, way down at 5,600 meters below the seabed. Now, to do this, you pump cement down the casing to seal it up tight. Pretty standard, right? Well, in this case, the cement job was totally faulty. It left voids and channels in the cement, essentially creating a high-speed superhighway for high-pressure oil and gas to migrate upward.
Okay, so the cement fails. But you've got to wonder, why didn't anyone notice? Well, this brings us to a massive operational failure. Before you plug a well, you conduct a negative pressure test to confirm the structural integrity of that cement seal. Basically, you reduce the hydrostatic pressure in the well to below the reservoir pressure and just watch what happens. During this test, there were glaring, completely anomalous readings. The kill line returns showed 0 pressure, but sensors inside the drill string were measuring pressure in excess of 1,400 psi. These readings were practically screaming that the well was not properly sealed. Yet 2 different teams on the rig looked at the exact same results and interpreted them differently. Incredibly, they attributed that 1,400 psi to a completely fabricated phenomenon that they just made up and called the bladder effect. They believed what they wanted to believe, deemed the test a massive success, and just proceeded with the abandonment. Which pivots us directly into Section 2, the human element. Because look, technical failures, they rarely just happen in a vacuum. They are almost always enabled by human decisions made under intense pressure. By April 20th, the Macondo well was 6 weeks behind schedule and a staggering $58 million over budget. There was an intense, totally palpable commercial pressure to finish this temporary abandonment and get the rig out of there. When you are bleeding millions of dollars, the pressure to just get the job done creates a really dangerous environment. It's an environment where flashing warning signs are rationalized away rather than properly investigated. For example, mud loggers, the guys whose entire job is to monitor well returns, had apparently ceased work 7.5 hours before the blowout. By the time anyone actually noticed the increased flow of mud rushing back to the tanks, which is a huge indicator that oil and gas are flying up the wellbore, it was way too late. And, this illustrates a tragic, recurring theme in engineering. The normalization of risk under commercial pressure is absolutely not unique to Deepwater Horizon. If we take a step back and look at the history of massive industrial disasters, think about the O-rings on the Space Shuttle Challenger back in '86, or the permit-to-work system breakdown on Piper Alpha in '88, or the Texas City refinery explosion in 2005, investigators find the exact same pattern every single time. Warning signs are present, commercial pressure is high. The risk gets normalized, and tragedy immediately follows.
All right, let's move on to the third layer of failure in Section 3, blowout preventer failure.
So even with a terrible cement job, and even with really poor human decision-making, there is supposed to be one final, absolute mechanical failsafe. During normal operations, if a kick of oil and gas travels up the well, the blowout preventer, or BOP, is your last line of defense. It's like a giant emergency brake. The BOP on the Deepwater Horizon was this massive stack of valves sitting way down on the seabed, rated to handle 15,000 psi. When the blowout escalated and mud started literally raining down on the drill floor, the crew tried to actuate the BOP. Later on, the automatic failsafe systems on the seabed should have triggered it as well. The whole system was designed to slam shut, deploying these heavy, blind shear rams to literally slice right through the massive steel drill pipe and seal the well completely. It was actuated, but it ultimately failed to cut the pipe and seal the well.
So why on earth did this ultimate failsafe fail? Well, post-incident investigations pulled the BOP up, tore it apart, and discovered a whole cascade of catastrophic mechanical defects. The blind shear ram blades were actually misaligned, which prevented them from cleanly cutting through that drill pipe. On top of that, the hydraulic pressure in the accumulators, which is the localized energy source that's supposed to drive those rams shut, was insufficient. And to top it all off, one of the two electronic control pods responsible for receiving the signal to shut the BOP was entirely non-functional. The equipment had just not been properly maintained to do the very thing it was designed to do on its absolute worst day.
That brings us to Section 4, Industry Aftermath. Obviously, the explosion, the loss of life, and the sheer environmental devastation forced an immediate, very hard look at how offshore drilling was even conducted. This single event completely dismantled the existing regulatory framework. Pre-2010, the U.S. regulatory environment under the Minerals Management Service, or MMS, was largely just a standard-setting approach. It heavily relied on the industry self-policing itself. The National Commission report later concluded that the MMS had fallen way behind the industry's super fast-developing deepwater technologies, and frankly, they had become complacent. So within a month of the blowout, the MMS was dissolved, gone. It was replaced by separate entities just to remove the conflicts of interest. You got the Bureau of Ocean Energy Management for leasing, and the Bureau of Safety and Environmental Enforcement dedicated entirely to safety oversight. The U.S. finally began moving closer to the really rigorous safety case enforcement approach used over in the North Sea after Piper Alpha, requiring operators to proactively prove their safety and risk management systems actually work.
Because of all these cascading failures we've talked about, the technical rules changed practically overnight. Safety and Environmental Management Systems, or SEMS, became totally mandatory to try and curb human error and enforce incredibly strict procedures. And on the mechanical side, rigs now absolutely require dual blind shear ramps for total redundancy, plus independent acoustic backups, so we are never relying solely on vulnerable hydraulic pods ever again. Furthermore, the industry had to admit it completely lacked the technology to quickly respond to a deepwater spill. They'd been relying on outdated booms and dispersants. This harsh realization led major operators to establish the Marine Well Containment Company, which acts as a central source for rapid, deepwater spill containment equipment.
And finally, let's wrap up with Section 5, Engineering Responsibility.
So we've covered the bad cementing, the intense commercial pressure, the mechanical failures, and the new regulations. But to conclude this explainer, I really want to bring this historical case study down to a personal mandate for you. Every single engineer faces a defining moment in their career. I want you to genuinely ask yourself, what will you do when the safe decision is also the inconvenient, expensive, or highly unpopular one? When a project is $58 million over budget, when your manager is breathing down your neck, and a pressure test comes back looking totally weird, are you going to invent a bladder effect just to make the problem go away? Or will you have the guts to hit the stop button?
Because what you really need to take away from all of this is that engineering is a profound responsibility. It is not just a technical exercise. Technical competence? That's just the bare minimum. The 11 people who lost their lives on the Deepwater Horizon were killed by a chain of technical failures. Yes, absolutely. But those technical failures were entirely enabled by human failures. True engineering requires the moral courage to stop work when things don't look right and to resist commercial pressure when lives are on the line. The government regulations and the fancy dual shear rams, those are just the backup plan. You are the first line of defense. So as you go forward in your career, ask yourself, when the pressure inevitably mounts, will your decisions ensure that everyone goes home safely, or will you allow the normalization of risk to write the next tragic chapter in our industry?